A 70-kilogram woman and her 35-kilogram son are standing at rest on an ice rink. They push against each other for a time of 0.6 seconds, causing them to glide apart. The speed of the woman immediately after they separate is 0.55 meters per second. Assume that during the push, friction is negligible compared with the forces the people exert on each other. A. Calculate the initial speed of the sun after the push. Okay, so let's start with A before going any further. So let's start by calculating the initial speed of the sun. So before we start, we can write down a few bits of information to help keep track of everything. The mass of the woman is equal to 70 kilograms. The mass of the sun is equal to 35 kilograms. The time is equal to 0.6 seconds, time in contact. The velocity of the woman after the push is 0.55 meters per second. 5 meters per second. So by momentum conservation, we know that the momentum before the push must be equal to the momentum after the push. So the momentum of the woman before the push, like the initial velocity, plus the momentum of the sun before the push must equal the momentum of the woman after the push plus the momentum of the sun after the push. So we know that before the push, they were standing at rest. So in both cases, these are their initial velocities were both 0. So this whole part of the equation can be omitted and replaced with 0. This whole equation is 0. So we know that the momentum of the mother, or the woman, plus the momentum of her son after the push must be equal to 0. So now we can just simply rearrange a few terms. We need to figure out the velocity of the sun. So we can just rearrange everything. And then we just need to solve for the velocity of the sun. And this is the expression for the velocity of the sun right after the push. So now all we need to do is just plug everything in. The velocity of the sun is equal to minus times the mass of the woman, 70 kilograms, times the velocity of the woman after the push, divided by the mass of the sun of 35 kilograms. So if you simplify this, you should get that the velocity of the sun after the push is equal to minus 1.1 meters per second. So I'm going to rewrite that and clear all of this. So the velocity of the sun is equal to minus 1.1 meters per second. And this is negative because he is going the opposite direction as his mother. So if his mother's going to the right, then he's going to the left. So now part B, so that was part A. Part B asks us to calculate the magnitude of the average force exerted on the sun by the mother during the push. So for here, if you remember the impulse momentum theorem, the given force times a given time interval is equal to a change in momentum. And again, change in momentum is equal to the final momentum minus the initial momentum. But since neither of them had any initial momentum, this can be ignored, and the change in momentum is simply the final momentum. And again, after the push, they both had equal momentum, so it doesn't really matter which one we use. So I'm just going to use the mother because it is a positive value. And the force they exert on each other is just equal and opposite. So the force times the time is equal to the final momentum of the mother. So the force, the average force, is equal to the mass of the woman times the velocity of the woman divided by the time that they were in contact with. So if we just plug everything in, it's equal to 70 kilograms times the velocity of 0.55 divided by 0.6. It's the time interval. So if you solve that, the force is about 64 newtons. So we can just round that off to 64 newtons here. So for B, the force is equal to about 64 newtons. And that's the average force exerted. So I'm going to erase all this. Now on to part C. After the initial push, the friction that the ice exerts cannot be considered negligible anymore, and the mother comes to rest after moving a distance of 7 meters across the ice. If their coefficients of friction are the same, how far does the sun move after the push? So here we can use work and kinetic energy to solve this. So we can say that the work done by friction, the force of kinetic friction. So let's say that this is the work done on the sun by the force of the kinetic friction, must equal to the negative of the kinetic energy of the sun. This is because they start with the kinetic energy, and all of that kinetic energy gets converted into like other forms like thermal energy until there's no more kinetic energy and the sun stops. And at that point, you can take the distance of how far he went. So we know that the kinetic energy is 1/2 mv squared. So we can just plug that in and substitute that in. That's squared. And work, we can break that even down. We know that work is equal to a force times the displacement. So we can use that to get rid of the work and say that the force of kinetic friction on the sun times the displacement of the sun must equal -1/2 times the mass of the sun times the velocity of the sun squared. Now we can break this down even more to the coefficient of kinetic friction. And I don't need to specify for the sun or the woman because they have the same coefficient of kinetic friction. Right? It says it right here. Times the normal force, which equals coefficient of kinetic friction times the mass of the sun times g, little g, the acceleration due to gravity. So now we can just plug that in for our equation there. So the coefficient of kinetic friction times the mass of the sun. This actually gets canceled, but I'm just going to write it for now. It's kinetic, the negative of its kinetic energy. These two cancel, so we can ignore that. And now we just need to solve for the displacement of the sun. So by moving everything over to the other side, get that the displacement of the sun is equal to minus the negative of the velocity of the sun squared after the push divided by the coefficient of kinetic friction times little g. So I'm going to write that up here to make more room. So the displacement of the sun is given by the negative of the velocity of the sun squared divided by the coefficient of kinetic friction times little g. So now we just need to figure out the coefficient of kinetic friction. And we can do that using the mother's equation. And we can use the same equation for the mother. Coefficient of kinetic friction. Again, masses cancel as we saw in the first equation. Times little g times the displacement of the woman or mother must equal to the negative kinetic energy. There's no more mass of the woman. And we can use this to solve for the coefficient of friction before plugging it back into there. So if we just solve for that, we get that the coefficient of kinetic friction is equal to minus the negative of the velocity of the woman squared divided by little g times the displacement of the woman. And we are given the displacement of the woman, so we can go ahead and plug everything in. So we get negative of 0.55 squared divided by g times displacement of 7. And I'm not going to go ahead and write this because it's a really messy number, and we're going to need to plug this exactly in for that. So all we need to do is just plug everything in to here. So you get negative of the sun's velocity squared, and anything squaring is still positive. I'm not going to go ahead and write this, but just know that we're taking this value over here and substituting that for this when we carry out our calculation. And we're going to hit times 9.8. Alright, so if I erase some of this, it's a little too much. Now, if you solve this, you should get that the displacement of the sun is equal to 28 meters. So that's equal to 28 meters. Displacement of the sun is equal to 28 meters. That would be our answer to this problem. But there is actually probably another way to think about it that's shorter. So you can just basically think that the sun has half of the mass, so it has slightly half of the kinetic energy, but it also has half of the frictional force and twice the speed. So it would go 4 times as far as the displacement of the mom. So he would be going 4 times 7 meters or 28 meters. So that's another way to think about it, but if you want to numerically calculate it, you can do so using the way I just done. And that is how you would solve this problem here.